This is Chapter 3, Weld 2520. Pipe weld 2, schedule 80 pipe, and I'm reading from page 14 where it says heat input, and it says the heat input is controlled primarily by the current setting. To some extent, the heat input can be controlled by the arc length. The amount of heat input that we put into the weld is directly proportional to the amount of amperage that we're running, and it's really a combination of heat input and how fast you're moving. If you know those two things, you can calculate the heat input in joules into the weldment. When welding, the heat input into the puddle is often controlled by the welding speed and by the weave or whip, as discussed further on in this book. However, more correctly, this is a matter of heat distribution. Unfortunately, it is not possible to provide exact recommendations for the current settings to be used in each case for the following reasons. Number one, the adjusting devices on all welding machines are not the same. One machine set at 90 amps may liberate the same amount of heat as another machine set at 130 amps. Based on that first statement right there, Western is an AWS accredited testing facility, but as part of that facility, we had to have the machines that we use in AWS testing calibrated to national standards. And they came in and they hooked our machines up to a bank that they were able to use to calculate the heat heat output of each of our machines to within 2%, and that's enough to qualify for AWS standards. Most of the machines, fortunately, that we have in the welding lab are very accurate, very close to what they read, especially those with digital readouts. Reading number 2 now, it says the age and condition of the machine will affect the heat obtained at a given current setting. Electrodes made to the same classification but manufactured by different companies may require different current settings to liberate the same amount of heat. The mass or thickness of the pipe must be considered because a larger mass will absorb more heat away from the welded area. The length of the cable in the circuit will affect the heat in the arc. For a given machine setting, increasing the length of the cable will result in less heat at the point of welding. Environmental conditions affect the current setting to be used. For example, a current setting made outdoors on a windy and very cold day may be different from the setting made indoors in a shop. And of course, that's simply because heat goes to cold, and if you have a cool wind blowing over the pipe, it's going to draw off that heat much, much faster. So, since there are so many reasons why current settings vary, it is common practice for welders to evaluate current settings by depositing a weld bead or beads on a piece of scrap steel. Conducting this evaluation beforehand is a very important step in making a perfect weld. For pipe welding, the evaluation should be conducted on plates in the vertical position. Weld the test plate uphill or downhill, depending upon the direction to be used in the pipe. The plate should be free from dirt and rust. Rust, when in contact with the molten weld pool, will cause undercuts on the edges of the weld. So before you start a weld, especially if you're outdoors, go ahead and run a practice speed and check your heat. And by now, you should have a fair idea of how to evaluate whether or not you have enough amperage and if the volatility of the puddle is sufficient for what it is you want to weld. Of course, in the flat and horizontal positions, you can weld at higher amperages than you can in the vertical up and overhead positions. So the advice here is simply to go ahead and make a practice weld prior to starting any type of production welding. Page 15, heat distribution. The distribution of the heat and the rate at which it is withdrawn from the weld zone are dependent on the following factors. 1. Conductivity of the work material, that is, its heat conductivity. What type of material are you welding on? Aluminum is going to heat up an awful lot faster than carbon steel is. 2. The mass of the metal surrounding the weld zone. How thick is it? Are we welding on 6-inch Schedule 40, or are we welding on 6-inch double extra heavy? 3, the paths available for the heat distribution. If you're welding near the edge of a piece of plate, there's no place for that heat to go, so it's going to heat up a lot more towards that edge. If you're welding in the middle of a pipeline, say a 12-inch standard pipeline, and you've already got the root pass in, well, now there's lots of places for that heat to go to. And then, of course, the use of the weave or the whipping technique. When compared to most other materials, all the metals are good conductors of heat. However, all metals are not equal in their ability to conduct heat. For example, aluminum is a better conductor of heat than stainless steel, as shown in Figure 3.2. The metal in the area of the weld will cool more rapidly in the case of aluminum than in stainless steel. Moreover, the heat will disperse throughout an aluminum plate far more rapidly. A large mass of metal adjacent to the weld zone will tend to withdraw heat from the weld zone more quickly than a small mass. That's the example I gave you with Schedule 40 and Schedule 80 pipe. Another factor to consider in estimating the rate at which heat will be withdrawn is the number of paths available along which the heat can flow. In Figure 3.4, the plates have the same thickness. If you look at Figure 3.4, that's on page 18. But the heat will be withdrawn more rapidly from the lap joint than from the edge joint, because the lap joint provides 2 paths or directions of heat flow as compared to 1 direction on the edge joint. So you want to take that into consideration as well. Turning over to page 20, the distribution of heat in the weld zone is affected by the welding technique. While welding, the electrode and the arc are sometimes deliberately moved in and out of the puddle of molten metal in a uniform pattern to reduce the temperature of the molten metal and to preheat the metal ahead of the weld. So if you're using your whipping technique, we're controlling the heat in the puddle, but we're also preheating ahead of where we're going. This technique is called whipping. When the puddle of molten metal is moved back and forth in a uniform manner across the weld joint, the heat in the area close to the weld is spread out. This technique is called weaving. It is used to spread the heat and to obtain a wider weld bead without maintaining an excessively large puddle of molten metal. Whipping and weaving will be treated in greater detail in later chapters. In summary, and this is really a brief little introduction to heat distribution, the welder must analyze the weld joint and estimate the directions in which the heat will be dispersed. He can then adjust the current setting on the machine to provide an adequate amount of heat to maintain the molten puddle of metal and to obtain the desired welding speed. If the weld joint causes the heat to be withdrawn rapidly, the current setting is increased and possibly the welding speed will have to be slowed down. On the other hand, if heat will not be dispersed readily from the weld joint, a lower current setting is used, and it may be necessary to use a whipping technique. So that's real brief on heat input and distribution. And of course, it's going to be affected by other factors as well. If you use preheating or any post-weld heat treating, preheating particularly would be important. And I can't emphasize enough that the thickness of the material being used is going to be an extremely important factor, and your joint fit up and your joint design also. So, if you have any questions on that chapter, speak with Jeff or I in the lab. Thank you.